Okay, yes, I want to talk about two different concepts. The first concept are tuple spaces, distributed sensor tuple spaces. And on the other side, there's a communication technology used to connect the sensor tuples, that is Bluetooth and as a fallback and background solution, IP broadcasting. So, start with an introduction. Ubiquitous and pervasive computing introduces a big amount of visible and non-visible low resource and mobile devices like smartphones, for example, with an exponentially increasing number of deployed embedded systems. So short time and short range device-to-device and device-to-service communication in such kind of ad hoc mobile networks is still a challenge. Most Internet of Things devices and smart sensors are connected via the Internet. Well-known fact. Using IP communication, UDP protocol, TCP protocol, HTTP, and so on. Data exchange with dedicated servers is performed that collects sensor information periodically or event-based. So this is the state of technology, the state of the art. Which data taxonomy can expect in ubiquitous and pervasive computing? That means in the IoT context and so on. IoT and smart sensor devices typically are sources of specially distributed and time-dependent small data chunks. We don't have big videos, like gigabytes of data. We have small chunks. Sensor data size is about 1 to 100 bytes per single data atom. It depends, of course, on the application. Sensor update frequencies are about 1 millihertz to 1 hertz. Sensor data has a limited lifetime, temporary data. Typically 1 to 1,000 seconds, just as a guess. So sensor data stream classes can be distinguished between event-based versus periodic versus sporadic. And sensor data with a special context in the special range can be typically expected in IoT applications with an accuracy about 1 to 1,000 meters, expected accuracy. So, and we have a sensor density about at least 10 sensors per square meter, exponentially growing. So here you see the big city, the smart city world, with a lot of applications. I don't go in detail. But what is important, we have a three-dimensional space. If we concern data, we have the data size of one data element. We have the frequency, one new data element per second, per day, or whatever. And we have a special context, a location range. For example, a building sensor measuring the crowd flow must have a special context, because if I don't know where the sensor is, the information is not usable. So this is the three-dimensional space of data we have to address to. If we think about the Internet of Things, we have to think about more. Here you see it, originally the intranet of things, that means very closed networks, then the extranet of things, that means the devices were opened and connected to external servers, then the Internet of Things, and finally, with this very important future Internet of Things and people. We talk basically now about the Internet of People. So the human-machine interaction is now very important in the IoT. What are the disadvantages of Internet-based communication? No, not always and everywhere available. It's still an issue. We need unique device Internet protocol addresses. Even with IP version 6, we need them. Address-based communication, this is the typical case in IP, with IP protocols. But indeed, we need data-based communication, data-addressed communication, data-related communication, not address-based communication, because the data is the important part, not the device. So we have a limited scalability. We need external organization services like a name lookup service, DNS, and whatever. Energy is a concern, especially in mobile internet, via cell networks, and so on. Loss of special context, still an ongoing issue, because the IP address is not really a measure for the special context. We have security issues. And even UDP is not optimized for small data transmissions. For example, a temperature sensor with 1 byte data payload. Yeah, and finally, we need routing with routing tables and so on. We need knowledge, some kind of knowledge about the network. So here you see the chirps are typically collected within propagator nodes. That means the data chunks bundled and pruned as necessary for transmission and then typically forwarded over the traditional internet. So here on the left side, we don't need the internet. On the right side, okay, it's clear. If we have services, servers, and so on, we need the internet. But not on the front end side. On the back end side, yes, but not on the front end side. And here you see the typical data flow in very small chunks, periodically sporadic, event-based, and so on. And we have mostly a collection and aggregation in propagator nodes. So what is the novelty of this work? We have data-based versus address-based communication. We use always broadcast versus unicase message communication. That means there are no device addresses required. Communication preserves the special context, either by using short-range Bluetooth broadcast communication or by mid-range UDP IP broadcast communication. And we have local processing. This is very important. Communication is controlled and managed by simple event-based agents, and they have direct access to tuple spaces, which organizes the data. So tuple spaces provide generative data-driven device interaction. And finally, we have a lot of tuple spaces, basically one tuple space on each device, and they are loosely coupled and distributed. And they spawn, and this loosely coupling is spawned by mobile devices and agents. So we talk about distributed tuple space and agents. A tuple space is basically a database containing tuples, and a tuple is just a loose collection of numbers of data or whatever. So the only measure of a tuple is its arity. That means the number of elements and the type signature. And this can be any type signature is supported, any number of elements. So each tuple space can be divided in subspaces, which only holding, for example, tuples of a specific arity, and the data type of each element of a tuple can be arbitrary. But in this work, only a subset is supported, namely strings, float, and integer. Yeah, and this is the basic concept for the data representation in this work. Here you see the basic operations, well known, for example, from Linda. 30, 40 years ago, it's a well-known distributed communication paradigm. We have out operations that store tuples in the tuple space, and we have input operations that consume, or read operations that copy tuples, data tuples from the tuple space. That is the basic concept. We have on the left side producer processes, producer process agents, and on the right side consumer process agents. And the roles can be vice versa. It's not fixed. So here you see the our software framework behind all this work is programmed in JavaScript. Here is an example of the direct access in JavaScript to the tuple spaces from the host application, not by, for example, agents deployed in the system. But you see the operations are directly implemented with a programmatically API. So it's very simple to store tuples here, for example, with the out operation, to listen for new tuples arrived in the tuple space, and so on. Here, for example, the notification is just a notification of all listeners that there is a new tuple, that this tuple is not stored permanently in the tuple space. So the other part, we have tuple spaces, we have agents, and we have the communication technologies. Now I talk about the second level, the agents. And agents here are simple functional units providing event handlers. They are event-driven agents. And agents just are functional code that listen to incoming tuple requests. And the agents can act as a bridge, for example, between communication backend and the tuple space, and they can perform filtering of incoming messages, and, for example, to decide to reply to requests. They can access the tuple space or discard messages. And of course, the most important part, they can act as a bridge between different tuple spaces. So here you see the basic concept, the agents and the tuple routing. That means here we have two devices or two communication endpoints. For example, here Bluetooth and here UDP. And each device and each communication technology has its own tuple space. It's just a temporary storage of data. And here you see the agent can bridge two tuple spaces. Here, for example, the Bluetooth tuple space, receiving Bluetooth messages with tuples or sending Bluetooth via Bluetooth tuples. And here the other, the UDP tuple space connected to the IP communication. And an agent can bridge two tuple spaces, can forward messages, and so on. So you see the agent programming interface very shortly. Please look in the publication, the paper. You see again here basically the structure, here the body variables of the agent. And here you see the event handlers. That means here I can select a specific tuple space related to a communication technology, for example, UDP and Bluetooth. And if there is a tuple received, for example, here consisting of two elements, then this event handler is fired. And here, for example, the agent is able to forward this tuple to another tuple space or to another communication device. Here, for example, Bluetooth. Yeah. So this is basically the concept. It can transform tuples and so on, or can discard these tuples. So it's very simple. It's just a reactive function with state here in the body variables. A little bit about security. Security is important, but I will show it next. The Bluetooth communication is very limited to the payload size, about 50-60 bytes. Very, very limited, or 80 bytes. So real security, classical security by SSL or whatever, can't be used. So what we are using is a symmetric two-way encryption with a private and a public key pair, but with format preserving encryption. That means that the encrypted message has the same length as the unencrypted message. So it's a very, very, very low level security, but it's the only we can put in the now introduced communication technology. First of all, the most important part, short-range Bluetooth, low-energy communication, using broadcasting only, not a traditional master device or a master-slave communication, broadcasting. Then, with higher payload possible, mid-range UDP IP communication, always in broadcasting mode. Yeah, and I already mentioned both technologies use broadcast messaging of packed tuple operations. So all the tuple operations can be packed in a message that is broadcasted. For example, here using Bluetooth communication, here you see the basic format with the sequence number and operation. Here you see the basic tuple operations, a signature, the type signature of the following data, and here you see only 32 bytes of payload data in maximum. This is a limitation of the broadcasting format of Bluetooth, which limits to 272 bits. So we support only core data types, integer 16, float 32 bits, and string and formal parameters for patterns, for example, for the read and input operation. So we have a short-range communication. That means in a range of 1 to 10 meters, typically covering single rooms or floors. Here you see the basic principle. A message is sent multiple times within an advertisement interval. We use the advertisement mode, well known by contact tracing apps, utilized in Europe, millions and billions of people. And we use the advertising mode to advertise these tuple messages. And a receiver, here we have the sender that sends the message again and again in a specific interval, of course, say 300 milliseconds or 500 milliseconds. And there's a chance that the receiver will receive this message. So it's a probabilistic communication. It's not reliable. It's just probabilistic. There's a probability that the receiver will receive message which was sent by the sender. And of course, all devices in the communication range can receive these messages. So the same principle with UDP-based broadcast communication in the intranet, of course, not in the internet. We broadcast in the same format the tuple messages. The range is typically larger, extended to, for example, a building environment. And UDP broadcasting requires typically wired connections. This is very important. Although Wi-Fi or VLAN is a radio communication technology, today all VLAN or Wi-Fi connections are always secured point-to-point connections. And Wi-Fi VLAN access points will not distribute or broadcast messages or broadcast packets. They do this on a really unreliable basis. So UDP is basically for wired connections, from beacons, computers, embedded devices, connected wired to the intranet of a building, for example. Yeah, here you see the concept. Here the wired UDP network. Here the Bluetooth communication. If two devices are in communication range, they can exchange messages just by advertising. Each device has a tuple space, each communication device, and we have agents that forward and bridge the tuple spaces. And most of all, a mobile device like a smartphone can carry tuples to another special location. This is shown here. Yeah, for example, this beacon here got an tuple data message or a tuple data or data tuple. And the agent forwards this via Bluetooth to a mobile smartphone device. And now the user is migrating to another floor or whatever, or other building, for example. And again, we have here a beacon. Then this mobile device carries this transmitted data tuple and can propagate it here in a new special context. So we have mobility of tuples by mobile users, or cars, vehicles, or whatever. At the end, a short use case evaluation. It's just a proof of concept, a decentralized light control on buildings based on user perception and negotiation. You remember at the beginning, I said, we don't talk about devices, we talk about humans and devices. Now, this distributed tuple space system or architecture is used to perform micro-surveys. For example, on a smartphone, asking users in a typically bureau environment, office environment, in a building, in a large building with large office rooms and so on, with hundreds of people, is the light condition okay? Can be, of course, also extended to any climate relevance, climate parameter, temperature, and so on. But here we focus on light. And so we have a very little survey that is propagated as a tuple and processed by an application on the smartphone that is then able to perform a short chat dialogue with the user, and the user asks just a question, is the light condition okay, for example. Yeah, and we can use, for example, the light sensor in a smartphone to get a physical measure of the light condition. So we perform distributed micro-surveys from a decentralized light control service. And we have beacons here, for example, Raspberry Pi 0 devices or 3 devices. And we have some servers that control the building. And we have VLAN, Wi-Fi, APs, and of course, wired communication and the Bluetooth communication, especially here between the Raspberry and the smartphones. So different agents negotiate light control in different areas of buildings. Agents perform sensing, light intensity, crowd flows, user activity, and mobile surveys via a small chat application. And the goal is to optimize the light illumination with respect to the user satisfaction and energy reduction. Here you see the basically setup. Here we have the rooms. Here we have beacons, for example, the Raspberry computer. Here are the mobile devices. They can interact via Bluetooth with the beacons. The beacons are connected either using wireless connections or wired connections. And so we have here the central light control service that control the light here in all the rooms. And what are the results? No, using the light sensor, the mobility assessment, using the accelerometer and gyroscope sensors of the mobile devices to get a measure if the user are moving or is just sitting in the bureau or whatever in the office, and the performed micro surveys providing the required user feedback, the satisfaction assessment, and the illumination conditions could be optimized with respect to both user demands and energy consumption of about 30% without negative user feedback and dissatisfaction. The Bluetooth low energy technology showed an average tuple loss of about 10% that can be achieved within a radius of about 2 meters, 30% in 5 meter radius, and some nodes can still communicate over a large distance up to 10 meters with a device density of 2 per square meter. The Tuple message sending times interval has no significant impact on the loss rate due to collision, for example, within a time interval, sorry, this is a mistake, of course, milliseconds, 500 milliseconds and 2 seconds. And with this small setup, of course, with 2 devices per square meter. And the number of nodes within the radio range will be increased. The loss rate will increase too, of course, due to collision. Please remember, we have broadcasting. Yeah. And broadcasting to LAN to VLAN did not work reliably, lost about 50%. So wireless communication using UDP broadcasting is not a good idea. Here's some statistics. Here you see the reception rate, very high in a short range, still high in 5 meter range, and interesting in 10 meter range, still available. Some devices can communicate. And you see here the interval time, the time interval where the advertisement packets were sent periodically has no impact on the reception rate. Yeah, to summarize, distributed tuple spaces were used to exchange data between devices, providing a special context. Smart devices access the tuple space by tuple message communication. The communication is connectionless and ad hoc by using low energy Bluetooth broadcasting. Mobile devices act as a tuple carrier that can carry tuples between different locations, not connected by any communication. And additionally, UDP-based internet communication can be used to connect the tuple spaces. Yeah, and finally, the Bluetooth low energy tuple space service enables opportunistic, ad hoc, and loosely coupled device communication with a special context. The typical loss rate is below 20%. Yeah, thank you for your attention. Any questions are welcome.